The first type of titration that we'll discuss involves a strong acid and a strong base. So just a little background, whenever you're looking at titrations, what you're looking at is you'll usually have a solution here, and this solution is what we will call the analyte. And then we also are adding another solution to this, and this solution is what we call a titrant. So whenever we perform a titration, in this first example we have 40 milliliters of 1 molar HCl, so that is our analyte, and we're titrating it with sodium hydroxide. So what we're going to do whenever we start looking at titrations is we're still going to use ice charts as we did with chemical equilibrium, but for titrations with the ice charts we usually start with moles first, and then we'll go on to using concentrations. So this first example, what we're going to do is we're going to break it down into 4 different spots. We're going to look at the initial pH, we're going to look at the pH before the equivalence point, the pH at the equivalence point, and the pH after the equivalence point. So the initial pH would be just like any other problem that we looked at with chemical equilibrium. So calculate the pH before the addition of sodium hydroxide. Well, what we'd have to do here is we'd recognize that HCl is a strong acid, which means it dissociates completely. So pH is equal to the negative log concentration of H3O plus, and we could just break this up into H plus and Cl minus, so we'd end up with negative log 0.100 molar, and the pH is equal to 1. So now, as we start to move on, we'll start to look at adding sodium hydroxide, and this is where things start to get more complicated. We're no longer just looking at an acid or a base dissociating. We're looking at adding a base to an acid or an acid to a base and the resulting effect on the pH. So this first addition, what we have is we want to calculate the pH after we've added 10 milliliters of 0.1 molar sodium hydroxide. So what we need to do is we need to calculate the moles first. So recall that molarity is equal to moles over volume in liters. So if we want to know the moles, we'll take the molarity times the volume. And again, the volume has to be in liters. So if we want to figure out our initial moles of HCl, or moles of H plus, what we would do is we take the concentration, which is 0.100 molar, times the volume. So recall that there are 1,000 milliliters in a liter. So we multiply that by 0.0400 liters. So to start with, we have 0.00400 moles, or some people would write this as 4 millimoles. So let's go ahead and write out our net equation. So we have H plus coming from our analyte, the HCl, plus OH minus, which is coming from our titrant. And keep in mind that the sodium and then the chloride ions are spectator ions, so they won't occur in the net equation. And this is forming water, which will not be part of our equilibrium expression because it is a liquid. So whenever we start to set up our ice chart for a titration, the first ice chart will use moles, not concentration. So we'll take this 0.00400 moles for H plus, and now we need to figure out how many moles of OH minus we have. Well, we could use that same equation that moles is equal to concentration times volume for the sodium hydroxide. So you should end up finding out that you have 0.00100 moles of hydroxide. So we have our ice chart set up like this. So once you have your initial molar amounts entered in, what you'll have to do is you'll subtract off the smaller amount, which in this case is from the moles of hydroxide. So our moles of hydroxide will be completely neutralized, and we'll be left over with a few moles of hydronium, or H plus here. So we have 0.00300 moles of H plus and no hydroxide remaining. So if you want to find the pH, recall that pH is equal to negative log of H plus. Not the moles, it's the concentration. So now we need to keep a running total of our volume. So the total volume is 40 milliliters from the HCl plus 10 milliliters from the sodium hydroxide solution. So we have a total of 50 milliliters. So whenever we plug this in, we'll have negative log, and then the concentration of H plus will be 0.00300 moles, which we got from right here, over 0.050 liters. What we'll end up finding is the pH is equal to 1.22. And what we should see as we are progressing with this titration is as we're adding a base, our pH should be increasing, which is what we found. The initial pH was 1, and then after we added 10 milliliters of sodium hydroxide, the pH has increased to 1.22. So now let's go ahead and look at the equivalence point. So what is the equivalence point? Well, the equivalence point means that you have equal moles. So equal moles of acid and base. So technically you wouldn't have to go through and calculate the moles of hydroxide since you know the moles of H plus already, but you could go ahead and plug in just to double check. Moles of OH minus would be equal to that concentration, 0.100, times that volume, 0.0400 liters, and that equals 0.00400 moles. So again, we'll set up our net equation. So we'll have H plus OH minus yields H2O. Set up our ice chart. So again, I told you that you would subtract off the smaller molar amount. Well, here it's the same, so it doesn't matter which one you subtract off. So whenever you subtract off 0.00400 moles from both species, you'll be left with 0. Well, what's the pH of pure water? Well, the pH is equal to 7. You could go through and use kW if you wished, but since you recognize that there's no surplus of H plus or OH minus, the pH is 7. Let's go ahead and calculate the pH beyond the equivalence point. So here you go through, you'd want to calculate your moles of OH minus. So plugging in, you should find that you have 0.00600 moles of OH minus. So our net equation is H plus OH minus yields H2O. So the initial for H plus is 0.00400 moles, and OH minus is 0.00600 moles. So an important point to make here is some people do this in a slightly different method. What I like to do is for the initial is to always start with the initial amount. So that's one way to do it. Other people would set up their ice chart and they would keep a running total. So instead of starting with the 0.00400 moles, they might realize that, well, there's 0 moles of H plus remaining whenever there's 0.004 moles of OH minus. For me, it makes more sense to just always start with the initial amount so then I don't make a silly mistake with addition and subtraction. So here, we'll go back to our chart and we'll subtract off the smaller amount, which in this case is from the H plus. So we have no H plus left. We have 0.00200 moles of OH minus. We'll need the total volume. So the total volume, well, we have 40 milliliters of HCl initially present, plus now we've added 60 milliliters of hydroxide. Make sure you aren't double adding the hydroxide as we're going. So we have a total volume of 100.0 milliliters. So now notice that what's remaining is actually moles of OH minus. So it'd be easier for us to find the POH. So POH would be equal to negative log of the hydroxide concentration, which in this case we'd have negative log of 0.00200 moles over our total volume, which we need to convert to liters, so 0.1000 liters. You plug this in and you find that the POH is equal to 1.70. But since we're asked to find the pH is equal to 12.30. So that's how you go through in a stepwise, systematic manner to find the pH of different steps in a titration. So we looked at the initial pH, we looked at something before the equivalence point, something at the equivalence point, and something beyond the equivalence point. So these are for the easiest types of titrations with a strong acid or a strong base, where you're only looking at H plus and OH minus. In a future lesson, we'll start to look at weak acids and weak bases with different combinations of strong acids and strong bases. And here we actually have to start worrying about Ka's and Kb values. So you might have multiple ice charts per problem. But to get started, we're only dealing with one ice chart, and no matter what type of titration it is, the initial ice chart will always be looking at moles, not concentration. So now I have another example for you. So why don't you guys go ahead and pause the video and try this on your own before I show you the solution. All right, so here's the solution to this problem. What you always want to do whenever you're solving a titration problem is to try to have an expectation for what your answer should be. So whether it's acidic or basic. So if you have a strong acid and a strong base, if you're starting with your analyte being a strong base, then you would expect, which it has to be true, that any time before the equivalence point, your pH would be greater than 7 because you have a basic solution. Anytime after the equivalence point, it will be acidic. And this is for a strong acid and a strong base titration. So as you're going through and calculating the moles, make sure you're keeping track of this. So here, just a quick rundown. We started by finding the moles of hydroxide. And then I found the moles of H+. And from here, I just set up 3 different ice charts to calculate the pH. And for each one of these, you'd plug in the moles, you'd subtract a smaller amount, and then you have to remember to find the total volume. And then you'll plug that in to find the POH or the pH depending on what ion is remaining. So go ahead and check your work, and if you have questions, just go ahead and email me.